In this lesson, we're going to look at Dalton's law of partial pressures. So if I have a container that has this many moles of one gas, and the pressure there is 200 kilopascals, and I have a same size container with that many moles of a second gas, and the pressure there is 500 kilopascals, and I have another container of the same size with yet another type of substance, and that has a pressure of 400 kilopascals. If I were to take all of those gases and put them all into the same container, so we're talking about the exact same type of container here, but instead of being in three separate ones, they were all together, then the pressure of that container with all three of those gases is just going to equal what is called the partial pressure of each separate gas. So all that's going to happen is those are each going to get added up. So 200 kilopascals, 500 kilopascals, and 400 kilopascals. So this is called Dalton's law of partial pressures. So the pressure of the particles of the green gas here is 200 kilopascals. It's still 200 kilopascals in here, but the total overall, because we also have the red gas and the blue gas, which are 500 and 400 respectively, our total pressure here is 1,100 kilopascals. So Dalton's law states that we add up the partial pressures to get the final pressure. So Dalton's law of partial pressures and air pressure. So if you are standing on Earth, the atmosphere is made up of oxygen, nitrogen, carbon dioxide, and argon. And we have the respective partial pressures of each. So 8 millimeters of mercury for argon, 3 millimeters of mercury for carbon dioxide, 590 millimeters of mercury for nitrogen, and 149 millimeters of mercury for oxygen. So the total pressure of the particles in the atmosphere would be the addition of the partial pressure of each of the separate elements or compounds. So 149, 590, 3, and 8. So the total air pressure would be 750 millimeters of mercury. So the partial pressure is if we have a mixture of different gases. The partial pressure is if we just had that one separate gas by itself in the container that it's currently mixed in with other gases, the pressure that it would exert if it were just in there on its own. So the same amount of that particular gas, but all the other gases removed. So that is the partial pressure of any particular gas. Now the mole ratio in the mixture of gases is going to determine the gas's partial pressure. So if I have twice the amount of oxygen as I do carbon dioxide, then oxygen would exert twice the amount of pressure that carbon dioxide would. So the total pressure of a mixture here is 97.4 kilopascals. And that is made up of 3 moles of helium and 4 moles of neon. So to calculate the partial pressure would be if I only had helium in there and if I only had neon. So what would be the partial pressure of helium and what would be the partial pressure of neon? So helium is 3 out of the 7 moles that are currently in there. So 3 out of 7 moles of helium, and we're going to multiply that by the 97.4. So 3/7 of the pressure comes from helium. So 41.7 kilopascals is the partial pressure of helium here. And for neon, we have 7 moles total, and 4 of those moles are neon. So 4/7 of the total pressure comes from neon. So that is 55.7 kilopascals is the partial pressure of neon. So Dalton's law then is that the total pressure of a mixture is equal to the sum of the partial pressures of each individual gas. Now, one of the things that we do to collect a gas in an experiment is to use a contraption where we have a tube leading off from our reaction chamber, and otherwise that is sealed off so that no gas can escape. And then we will often have a condensation tube, so it's a double glass tube with cold water running in between the 2 layers of gas to cool down the gas to potentially turn it into a liquid and bring it down here. So when that is happening and this gas is being bubbled into here, we're going to have some displacement happening, but because we have water in here, in this case, hydrogen is the gas that's being produced. There's also going to be some water that evaporates from this container that has water in it. And so we can determine that based on the vapor pressure of water that's going to exist at any temperature. So if, for example, it's 27 degrees, then the partial pressure for water is going to be 3.6 kilopascals. So we can use that and Dalton's law of partial pressures to determine the pressure of the gas being produced. So here is a closer look. So if I have my reaction chamber and the gas that's being created will come along into here and it will bubble up into this test tube, and so I've got a certain amount of gas being collected here. So in here I have an overall pressure of this gas that's being produced, but also some of this water is going to evaporate and become a gas. So the total pressure is going to be a combination of the pressure from the water vapor and also the pressure of the gas that is collected. So the partial pressure of the dry gas is going to equal the atmospheric pressure, subtract the vapor pressure of the water, which we can get from this table. So if I have 325 mils of hydrogen gas that's collected over water at 22 degrees Celsius, what is the pressure of the dry gas if atmospheric pressure is 94.4 kilopascals? So I'm going to need at 22 degrees Celsius, the partial pressure of water is 2.6. So I get that from the table. So the partial pressure of the gas is the atmospheric pressure, subtract the partial pressure of the water vapor. So atmospheric pressure I have there, and partial pressure of water vapor we looked up in that table, which was 2.6. And so the pressure of the gas collected then is equal to 91.8 kilopascals.